Our next speaker is Tom Walz. He uses biochemistry, biophysics, chemical biology, and structural biology in the laboratory of molecular electron microscopy to understand macromolecular complexes and membrane proteins and lipid environments. Something that is of note for Tom, that he likes all types of ice cream, but more importantly, that he's worked in the field of cryo and used several different modalities. He has had one of the first sub-2 angstrom reconstructions before single particle was in vogue. And something that he'll be talking about is not only a blast from the past, but a lot of these methods still hold true today, even though we use a different way of preparing samples. So Tom, without further ado, the floor is yours.
So thank you very much for introducing me. And it's a pleasure to be here. And the purpose every year for me coming here is to convince the organizers that they do no longer have to invite me. And every year I try to make a stronger case why this topic is really not necessary anymore. But so far I failed every year. So I'm supposed to talk about validation methods. And to me, this is really something from the past. As Rich said, the methods are just developing so quickly that almost nobody these days ends up in this weird resolution where you really cannot be sure whether what you have is correct or not. Most maps at least come to 6 angstrom, you will see alpha helices, so you're pretty sure that your map is correct. So why they think I still need to talk about this is actually beyond me. And so rather than talking about validation, I usually just give an overview of single particle electron microscopy, and maybe from my perspective, and maybe also reinforcing some of the things that Rich said about resolution and these kind of things. So the reason why validation methods used to be important is that there was a dark secret about single particle electron microscopy, and that was that no matter what data set you used, no matter how you process it, you always got a 3-dimensional map. So that was really great. The bad thing about electron microscopy is that any data set, no matter what method you used, you got a 3-dimensional density map. And so that ended up with the question, what you actually do, this density map, is it going to be correct or is it just nonsense? And so this is really particularly problematic when you have low resolution, when you don't see alpha helices, when you don't have structural features that help you to guide you to actually know whether your map is correct or not. And so the famous example, and this is now 2 decades ago, are these 4 structures of the IP3 receptor. And so these are 4 groups that use pretty much the same protein and use their own programs to develop maps of the IP3 receptor. And so all these 4 maps are supposed to be the same protein. The only thing these maps have in common is a 4-fold symmetry, and that's because it was imposed during the reconstruction algorithm. So the saying at the point was at least 3 of these maps are incorrect. And as you will see, all 4 of them were actually incorrect. And that was at a time when single particle electron microscopy really got a bad reputation for putting out these structures that really didn't mean anything. And we are way beyond this at this point, as you all know. But anyway, this was why it was important to try to figure out the maps that you create, are they meaningful or not. And so just an overview over how you get a EM structure, as you have heard now probably many, many times. You start out with your cells that express your protein or your complex, and you use expression purification to get your protein of interest. And then you prepare it for the microscope. It has to survive the vacuum, so you vitrify it typically. You get a grid with your vitrified sample. You then take images of your specimen. You get very noisy 2D images. To improve the signal-to-noise ratio, you pick particles, you align them, you do 2D classification. You now get much better 2-dimensional averages, which have a much better signal-to-noise ratio. Now you have these 2D averages, and you try to reconstruct a 3-dimensional view. So this is a 3D reconstruction approach. And you end up with an initial 3D map, which is going to be very crappy because you more or less just guess what the orientation parameters are. And these days, very often, you actually go directly from the individual particles to a 3-dimensional reconstruction. And once you have this initial map, you try to improve the orientation parameters. You do 3D classification. You end up with final 3D maps, 1 or more. And that's when you can start to interpret your map, and you dock in structures, you do model building. And so the actual electron microscopy is really just the specimen preparation and imaging. In my opinion, these days, the most important part of a cryo-EM project is really the molecular biology. Image processing are many different ways that you can go about it, but these days you almost always get a fairly reliable structure with these modern programs. And then you interpret it and you get your three-dimensional models. And what I'm supposed to be talking about is a validation of the three-dimensional map, which, as I mentioned, I don't really think is necessary, because once you see alpha helices or even side chains, you pretty much can be certain that you're correct. I'm not going to talk about validation of the 3D model. That's a different topic, and I think that's covered by somebody else. And these days, you actually can use the three-dimensional model, the atomic model, to validate the map. So you build and validate at the same time. But what I usually think is that the validation process really starts from the very beginning. The entire workflow that you do, you should validate and optimize as you go along. As you do that, you can be fairly sure that at the end, when you get your map, it's going to be correct. And so I'm going to talk about all these individual steps and just give you my opinion about some of those. And like with Rich, please ask right away. Don't wait until the end. It's much more fun when you ask. And so you start out with cells and you purify your protein. And there's a lot of issues that you can have with your protein. So the most common one is that you have heterogeneity. This falls into two classes. You can have compositional heterogeneity. You have a complex where subunits fall off. And then you have a conformational heterogeneity, which means, again, you have two different versions of conformational heterogeneity. One is quite easy, where you have distinct different states, and you can try to classify these states out. A much more difficult problem is if you have a continuous heterogeneity, continuous movement, if one arm just constantly moves in any way it wants. And this, to this day, is still a very difficult problem to deal with and can really limit the resolution that you get in your map. And then something that I want to mention is that a lot of people use cross-linking, either by just using glutaraldehyde or more fancy using graphics, which is a fantastic method. But when you cross-link, it's a good idea to check what cross-linking actually does to your protein. And so the issues that you have with this sample is that what Ed mentioned before you really try to do a cryo-EM structure, it's a really good idea to try and understand your sample as good as you can. So the usual things are gel filtration chromatography, and the one thing that I really believe in is negative stain electron microscopy. So before anybody in my group is allowed to do cryo, they have to do negative stain electron microscopy. The good thing about this is that you get fairly good contrast of your individual particle due to the stain. But even more important, you force, or in most cases, your particle will absorb to the carbon film in a preferred or a few preferred orientations. So if you now see all kinds of different shapes on your grid, you can be fairly sure that you have heterogeneity. So it's a very simple way to see how heterogeneous your sample is. And if you do see heterogeneity, we usually calculate two-dimensional averages just to get a better contrast, a better signal-to-noise ratio, and that allows us to assess what kind of heterogeneity we have. Do we have compositional, conformational, what kind we have? And then, as Rich said, we do whatever we can to try biochemical solutions to our problem. Small molecules, inhibitors, ligands, whatever you can think of, different buffers. So if you optimize a sample biochemically, you will have much less problem later on if you try to get a structure. But these days, you can also computationally purify your complexes, you can purify different conformations and so on, as you just heard. The techniques, the approaches you have these days are really, really impressive. But still, as good as the sample is, you go in, the easier it will be for you to get structures out of it. So we invest quite a bit of time to optimize the biochemistry. And then if you have a chemical, if it turns out that you need chemical fixation, which actually happens quite often for us when we look at complexes, we really always also look at the uncross-linked complex. And the reason for that is, here's an example. This is a so-called tethering complex. It's a Hobbs complex. And it's not easy to work with. And so a group has used graphics to prepare the sample, and you get these really beautiful particles and negative stain. And they got these very nice 2D averages. The problem is that those don't really mean anything, because if you do the same complex without cross-linking, the sample looks really crappy. It's a real pain in the ass to work with it. But once you calculate averages, you can see that you have all these flexible legs that come out of this complex with this central globular density. And what cross-linking does is it just basically cross-links this leg to the head domain and balls up these legs. So now you get a much better density, much better looking particles, but they have nothing to do with the actual biological molecule that you're looking at. So only when even just a few particles in the non-cross-linked sample look like the cross-linked sample, you're much safer. But if none of the non-cross-linked particles looks like the cross-linked particle, then cross-linking is probably not the way to go. So if you prepare specimens, you vitrify your sample, and you have the typical, so a lot of you have probably had these issues. You either see no particles in the ice, which is very annoying, because you have beautiful particles in negative stain, or you have a lot of beautiful particles, but then you try to calculate averages, everything looks the same. So you have significant preferred orientation. These are the two most typical issues that you have. And if you have no particles in your holes, it typically means that the particles like to absorb to the carbon film much rather than they go into the hole. And there are all kinds of different solutions to that. You can increase the protein concentration just to oversaturate it. You can double blot, which means you apply the sample, you blot it off, and now you have covered all the binding sites on the carbon film. Now you come with a second time, and now the particles are more likely to go in the hole. You can use thin support films, that's probably the most common way these days, especially because graphene oxide grids now, graphene oxide layers, don't introduce a lot of noise. So these are very nice films to use. And then there have been different ways. There have been PEG-treated grids, so that basically pacify the carbon film and the particles have to go in the holes, or you can use cold grids. So all kinds of ways that you can force. Yes? Yes, very unsuccessfully. It never worked for us. But I think, Rich, you did double plotting, right? For you worked.
In one case out of maybe 5 or 6, and
Yeah.
when it did work, it worked great. The other times, it doesn't work. And it's similar to all these other things that I mentioned, that they're further down the trajectory, but when you're desperate, you just use whatever you can.
Was it just like 3 microliters blot, 3 microliters?
3 microliters blot, wait an hour, 3 microliters blot,
Wait, what?
an hour.
You want to dry it.
You want it to be totally dry.
You need to dry the
So
protein.
protein was likely entirely denatured, but it was there because it didn't dehydrated. But once you added a second layer, essentially you're coating the carbon with background protein.
Not like BSA that just instead of your person.
So other people have proposed that as well. The disadvantage is BSA doesn't necessarily denature when it dries, so you end up with a ton of BSA coming back.
Okay.
Here, if it denatures, it's probably going to complete most of the complexes we work with aren't that stable. So once they're dead, you're reversing it again. So we won't mix that. We won't have a high background.
Okay.
And have you tried backplotting? That's one. And I've heard a lot, but when I tried, I never get the solution to go to the back.
Yeah.
I don't know how to do it.
Never worked for us.
Never even tried it. The only thing I ever saw with that is a lot of trapped carbon.
Yeah, I don't know where this comes from. That's not a good idea. But try. So try anything you can think of.
Didn't go through, you know. Like
Yeah, so
people have to globally check both sides or to trick the bed down, but yeah. No, they go for sort of but there's a person called her name is Sarah from Watch You Group, and she's done it, but
So, as Rich said, there are many, many ways to go, and you probably start with the most obvious one, which would be you increase the concentration, then you use a graphene oxide film, and as you get more and more desperate, you try all the other things.
There's an infinite number of permutations that you want to start with the ones that are most likely to succeed.
And then the other thing is that you have preferred orientations, and as Rich mentioned, this is because of the alignment of the air-water interface. And there are also a bunch of ways, and the problem with this is, of course, that if you lack certain views, your map, the resulting map, will be anisotropic in resolution, and that can create problems when you build models. And so also all kinds of ways to get rid of this. The most common way these days is to use a low concentration of detergent, which will change the tension of the air-water interface, and you will have more luck to keep the proteins in solution. You can use carbon films or graphene oxide layers. This is commonly done for ribosomes. It helps you get some alignment on the carbon film, but the alignment effect of the carbon film is much less than the aligning effect of the air-water interface. And then for some reason that Rich just explained to me why you can use gold grids. I never quite understood why gold grids would change the orientation, but they do. That is actually something that does work sometimes. And then when you, yes?
I increased pH from 7.5 to pH 9, and I get a lot of.
That's very interesting because you go exactly the opposite way that I would go. I would go pH 6.
The IR of my protein is 8.4, so I went to pH 9, and
So that's the thing about Singapore. That's your protein, and it works for your protein. It probably wouldn't work for many other proteins. The reason I go to pH 6, or why I say that, is that Holger Stark did a really beautiful analysis to look at different buffer components, how they affect the stability of complexes. And the one thing that has the biggest effect is pH. And typically a low pH below 7 actually stabilizes complexes for whatever reason, but that was the finding of this paper. So that's why I would have gone to 6 rather than to 9. But if you have a very basic protein, that's a different issue. And so if you tried everything you could think of to get your particles into the holes and get a random orientation, if none of this works, as Rich also said here at NYSBC, Spot-it-on was developed. And that has really helped with a lot of cases that you can actually get particles into holes and you can get random orientations. Not always, as usual, nothing is a silver bullet, but Spot-it-on has been very useful. And the other thing, when even Spot-it-on doesn't help you, these days you can even tilt your grids in the microscope. And trust me, from people who have tilted grids in the olden days, it's not something you wanted to do. Because once you tilt and you illuminate it with an electron beam, you put charge on the sample, you build up an electron cloud on your sample, and that will deflect your electron beam. So almost every image that you take of a tilted specimen will be blurred out and kill your resolution. But now with direct detectors, you can counteract the blurring by motion correction. So if you really get desperate, you can now even collect data from tilted images, from tilted specimens. It's going to be still a little bit more painful, but it's totally doable. But I think even people here who developed it recommend you to try everything else first before you start tilting a specimen. So basically, when the electron beam hits your specimen and you start to hit electrons out of your specimen, you have knock-on effects, and this creates an electron cloud. So this is what people think. I don't think it's actually proven, but that's the most likely thing that helps. So you will get the charge no matter what. If you have an untilted specimen, you will also get electron charge. But this cloud in an untilted specimen will just create a lens that will just change the point where you focus your beam. But if you have a tilted specimen and you have an electron cloud, now you actually start to deflect the beam. And as you deflect, you blur out your image. And so that's why it's always been very painful to try to take images of tilted specimens. And so that's just one of many examples. This is a very beautiful triangular complex, beautiful images. You calculate average, every single average looks exactly the same. So that basically kills you, but the moment you put in some detergent, the images don't look quite as nice, but now you get different averages of different views, and now you can calculate a three-dimensional density map. So that's probably the most common thing that people do, just add some detergent. And if this doesn't work, you can try graphene oxide film, and that typically takes care of the problem. So you have now a grid with your nice specimen. You take 2D images, and in the olden days, before we had direct detector, imaging was a problem. And the problem is that we have low contrast, and we introduce beam damage, and we also blur our images. And so the basic problem is that all our specimens, every biological specimen, DNA or protein, is a very poor electron scatterer. So you get very, very few scattering events, and what this means is that you want to increase your electron dose so that you produce more scattering events, you create more contrast. The problem with this is that our specimens are also exceptionally beam sensitive. So as we increase the contrast, we get more and more beam damage to a point where the whole structure collapses. That's obviously also not something that we want. So we want to actually use a low electron dose, and that was always the problem that we had in the olden days. How much dose can we tolerate so that we can still see our specimen, but we don't create too much damage? And the thing is that poor signal you can compensate for by averaging more particles, so you can build up the signal. However, once you damage your specimen, this information is lost and you can never recover it. So what we used to do was to take images with very low electron doses and then use averaging to try to improve the contrast. But that actually created a limit for us, because if you use a certain limited electron dose, when the protein gets too small, we just no longer create enough scattering events so that we no longer can distinguish what is a particle, what's the background. So that's why in the olden days you had to have fairly large complexes that you could see them in the eyes. And also because it was very noisy, the images had to be very noisy because we couldn't use so many electrons. We had very noisy particles, and those were very difficult to align. And the alignment, the precision of the alignment decides how high resolution you will be able to get. So that was really the problem at the time. We could not get images with very good signal to noise ratio. And this problem has pretty much been fixed now with the DDD cameras, and that has really, that's the transformation in electron microscopy. You can now get much, much better signal to noise ratio, and all the signal is there that will allow you to actually do all the alignment. You can see small particles and so on. So nowadays we can collect fairly long movies, and we know that at the end of these long movies, the frames, the specimen will be damaged. But we can simply resolution filter it and filter out the high resolution information of the later frames because those are damaged. But we can still keep the low resolution information, and that will increase our low resolution contrast, and that's what you need to align and to classify and all this. So nowadays we can, and obviously you do also motion alignment and all this. So with those kind of data, it has really totally revolutionized single particle electron microscopy. And even the people who have worked on these cameras were totally surprised what a transformation that really created. Not just as everybody knew that you would get a better signal to noise ratio, but nobody realized what a difference this would make to all your image processing. And so the whole field was actually taken quite by surprise how well this all worked. Yeah.
What is a DDD? Is it similar to like a direct electron?
Yeah, it's direct detection, direct electron detection device camera.
Oh, okay.
So it's a direct detector. All right, so imaging these days is typically not the problem anymore, especially if you have centers like this. They know how to collect data for you. So that's the reason why we don't use you. No, they do a fantastic job collecting data, so we are not typically worried anymore about data collection. So now you have your 2D images, and you pick your particles, you align them, you classify, and you end up with 2D averages. And there are issues that you should be aware of, and that's part of best practices, how you should pick particles, because there's a real issue with model of reference bias, and I will talk about this in a second. In addition, in the olden days, also when you do 2D classification, you have model and reference bias, but in the olden days, it was also kind of difficult to figure out how many 2D classes do you want to calculate? Do you want to calculate 100, 200, 500, 50, 10? So it wasn't clear how many you want to calculate. And if you didn't give enough classes, you ended up with heterogeneous classes, which still had heterogeneity within this population. And the other problem was if you have rare events, if you have rare conformations, rare views, if you don't have, even if you have enough classes, very often those rare views get sucked up by more populated classes. So there is a chance that you actually lose these low probability occurrences. I should say that these days, 3D classification has become so powerful with all these different cryospark and rely-on ways that 2D classification has become much less important. So most of us just use 2D classification to get a first read of what your sample looks like. Are you going to see secondary structure or not? And you want to get rid of all the really clearly bad particles, which is the ice contamination, the graphene oxide layers, the edges. But other than that, you're much better off leaving more of the blurry classes in your data set, because then in the 3D classification, you can take care of this. So 2D classification, just get rid of the worst particles, but don't do too much with it. But even then, one problem that you should think about is this model bias. And so there's a very famous example. So these are 1,000 images which are pure noise. There's no information in these images, nothing. But if you now take a reference, Albert Einstein, and you align these 1,000 noise images to this reference image, you get the ghost of Albert Einstein. And so this is known as Einstein from noise. And the problem is that even though there is random noise in there, it's random, it will try to align it to your reference. And so you will create your reference even out of pure noise. And this has been a problem not too long ago, actually about 10 years ago now, where this structure of the HIV envelope protein came out. And it was really a major splash, because in 2013, before direct detectors and all this, they went around showing the structure at 2.3 angstrom, something crazy like this, with a side entry holder that was moving like crazy, no motion correction. And so people got very excited about this, not the real electron microscopist, but the rest of the world thought, well, you now can do atomic structure with this. But if you looked at these images, you can really hardly see anything. But then when you look at the 2D averages that they showed, they were incredibly detailed. And so with those, they were able to get the 2 angstrom structure. But the specialists in the field, like Richard Henderson and Sriram Subramaniam, and the third one was who, I forget, they looked at this structure and they published papers in PNAS, basically detailing why this is nonsense. And so one thing was, for example, from Richard's paper, he took these 6 particles, calculated an average, and then changed the contrast, and suddenly you get all this strange density distribution, which cannot be if you just average 6 particles. This should not happen. So they did something weird with these particles. And the second thing is, a protein of the size of an nth protein is beta-galactosidase, and you can see the really nice contrast. So there's probably nothing really in this. This is probably all noise. And what turned out later on is what they did. They took a structure of the nth protein, did not resolution filter the reference, picked all these particles based on this reference, and then calculated averages from these particles, which ended up being exactly the reference at very high resolution. So all this was basically pure noise being aligned to the reference. So that's a real problem. And so if you want to be safe, and what you really should do, is the first time you have a new sample, you don't know what you do, pick them without templates, just with a Gaussian blur or even by hand. Nobody wants to do this anymore, but don't use templates. Don't assume what your sample is going to look like. And then when you have averages from this first, then you can use those templates to pick your particles, but they will come from your own data. Don't really Yes?
The Einstein reports that they just pick random spots in the micrographs as the particles.
I don't think they had many real particles in there. I think.
Outside the previous slide.
Which one?
Sure, like for the particle picking, they just pick random spots in the micrographs.
No, they used a template. So they had a very good template of your protein. So you have very good contrast. And then it just looked anything, even these broken down particles, which look somewhat like your reference.
So I'm asking just the pure, like for the sake of getting Einstein.
Yeah.
That was synthetic data. They used, I understand, yeah. So they used the Einstein as a template?
Yes.
Okay.
There they used Einstein as a template, pure noise images. Here they used their real structure as a template and picked very, very noisy, crappy images. It's not pure noise. There are contrast variations, but they're probably meaningless. In the end, they still, to this day, I don't know how they got a 6 angstrom structure out of this, but they did, and they published it. So it's a good idea that you try, especially if you don't know what your protein looks like, use your own data to create the references that you use later on to pick the particles. So now you have 2D averages, and you have to make an initial 3D map out of this. And that's one of the big things in cryo-EM. You have only projection data, but you want to understand the 3-dimensional structure of your protein. And that's actually a tricky bit. Not anymore, but it used to be a real problem to do that. And so very often, like in the IP3 receptor, you ended up with incorrect structures. And the major reason for that was that it was an underdefined problem how to get a 3-dimensional structure out of 2D projections. And you could have heterogeneous samples, but you don't notice that, and you take all these different structures and you try to make one structure out of this, which will go wrong. You might have missing views, and just a reconstruction algorithm might go wrong and give you a wrong structure. And so the first way that people have actually done and reconstructed an initial map out of 2D projection was called the random conical tilt reconstruction. And this was done in negative stain where you have a single or a few preferred orientations. And so you have your protein on the grid, you take an image, you get your projection, and then you tilt your specimen. And when you tilt it and take an image of tilted specimens, you get different views. The nice thing about this is the tilt of your protein is defined, so you know this angle. In addition, you took 2 images, one at 0 degree and one tilted, and so from the 0 degree, you know the angle relative to the tilt axis. So the geometry of those images or these particles were totally defined, and so it was very easy to assign the orientation parameters, and that allowed you then to basically align these projections in 3D space in the right conformation orientation, and then you just shine light through these projections and they will carve out a 3-dimensional reconstruction of your protein. So that was the first way how people defined a 3-dimensional map, and that there's no problem with the algorithm. It will give you the right thing. Had different problems because you needed the preferred orientation. That was typically negative stain. When you negative stain a specimen, you get collapse of the specimen. So you had specimen preparation artifacts, but you had no artifacts with the algorithm to reconstruct it. Now, in cryo-EM, it's different. All your particles are ideal in different orientations. And so for each of these particles, you have to define 5 parameters initially, 5 orientation parameters, x, y, where is the protein located in your image, and then the 3 Euler angles. And once you have all these parameters, then you can recombine the projections into a 3D map. So that's the trick that you need to figure out. And that was very difficult. That was not an easy feat. And in the beginning, the first way to do this was by angle reconstitution. And the principle was you found 3 projections that were perpendicular to each other. And that was your anchor set. And then you used these so-called sinograms to build in additional projections into this framework formed by this anchor set. But the problem is immediately clear. How do you know what 3 perpendicular projections are of your protein if you don't know what the structure of your protein is? So if you have a very well understood protein, then that might work. But in many cases, this algorithm actually ended up giving fairly nonsensical structures. And that was one of the reasons why many of the structures at the beginning were not reliable. And so this is actually work from Rich. This has changed with a program. We used it in Viper, but it was initially introduced with a protein called Simple. And it was a very simple change that completely changed everything. But before I can tell you how you now get very or fairly reliable initial models, the next thing I have to tell you is refinement, 3D refinement. So what an initial model is supposed to do is not give you a wonderful resolution, but it has to give you a shape that is pretty much correct. And then you can just refine the angular parameters, CTF and all this, and you will get to higher and higher resolution. But the first thing is you have to improve the angular orientation parameters. And the way you do this is you have your reference model, your initial model in this case, and you calculate a series of reference projections where you know exactly what the angles are of these reference projections. So now you end up with a stack of reference projections where you know exactly what the angles are for those. Now you have your experimental projections, your single particle images, and they're going to be very noisy, so you don't see the particle nearly as well. And what you're trying to do, or what you do now, is you cross-correlate this one with all the images in the stack, in the reference stack, and you end up with a stack of cross-correlation values, which basically tell you how good each of the reference stacks correlate with your experimental stack. And so what everybody would now obviously do is take the one which has the highest correlation peak, so that is the best correlation to your experimental stack. And so you use this one, and because you know the angular parameters for this particular correlation, you can now assign these angles to the experimental projection, assuming that you improve the parameters for this projection. And now you can align it in space, and you get, suppose, a better angular positioning of your projection. You do this with all your experimental projection, you get better orientation parameters, you do the back projection, you get your new model, and this new improved model goes and becomes your new reference model. And so you iterate this until you no longer improve this. So this process is called the steepest descent, and which means you have a very, very fast improvement of your density map. The problem with this is if your initial model is crap, you now have reference models of crap, and they will try to align this experimental to a crappy model, and so you get more and more features of a very crappy model, but you don't get your correct density map. And so it was a very simple change in this algorithm that changed everything. And so you do exactly the same up to that you get the cross correlations of all your you do a cross correlation of your experimental projection with the stack of reference projections, but this time you don't look for the best one, you just look the first highest one. So the first one is not good, the second one is better, and the third one is worse again. So now you take this one, you don't care what is coming behind. So now you take this one and you align these orientation parameters to your experimental projection and do the same thing again. What this means is that you no longer drive your alignment only exclusively towards your model. You have some stochastic element to it, and that allows you to actually get away from total model bias. And doing this, which is now implemented, I think, in pretty much every software package, with this one, you now get fairly reliable initial models, and that's really a major breakthrough in the image processing that we use. Yes?
Can you clarify, what are we looking at exactly in this stack of CTFs?
Okay, so basically you have the stack of references, and you have experimental. And when you correlate, when you do these cross correlations, you basically start out with cross-collating or multiplying, I actually don't know, multiplying.
So real space is just multiplication. In real space, it's cross-correlation.
Okay, so you basically start with an overlap of just one pixel, and you see how similar are these. You move along, you calculate another correlation, and so on, and you do this over the whole image, so that you end up with this image the same size, but every pixel now tells you how well is the correlation, the similarity between these two images if you would align them in this way. And so this is only shown in 2 dimensions. You have this actually in 3 dimensions. You have 2 dimensions, x and y, and the intensity tells you how well it correlates. And so this cross-correlation peak tells you how to align it and which one of your reference stacks aligns the best with your experimental image. Yeah? It is a stack. I just show it for one of the experimental. You have 10,000, a million, whatever you have, but I can't show them all. But you're right. You do this for every single experimental projection that you have. The same thing. So here you have at least 3. Anyway, so this very simple change from steepest descent to stochastic hill climbing really revolutionized initial model generation. And so now you have the initial 3D map, you do 3D classification refinement. Refinement, I just showed you how you do it. And the problem that you have with this is reference bias, as I mentioned. This has reduced by stochastic hill climbing. You can still overfit, and then one of the big problems that Rich already mentioned is resolution. People get very hung up on resolution. So what you do here in 2 dimension, if you do a 2-dimensional alignment with noise, the same thing happens here as well. So these references are actually your Einstein that you align your noise to. So this used to be, when you tried steepest descent, this was a very difficult step. Now with stochastic hill climbing, it's much better. So now let's talk about resolution. Rich did a fantastic job explaining what we do. But basically the way that we determine resolution is by splitting the data set, making 2 independent maps, and then use this particular formula where we basically end up looking at the correlation between these 2 maps in a resolution dependent manner. So at very low resolution, these 2 maps are probably very similar, so you get a high correlation, but as the features get smaller and smaller, it's more and more different, so you get less and less correlation. And so that's the Fourier correlation curve. And there's very little arguing, I think, about how you calculate this. The argue comes where, if you have this curve, where do you cut it? How do you decide what your resolution is? And the first criterion was FSC equals 0.5. And that was a simple thought that when the signal is about as low as the noise is high, at that point you become a little bit iffy whether the signal is still meaningful. So you just go and cut this curve at 0.5, and that gives you a certain resolution. And then later on, a few years later, Richard Henderson came with this FSC equals 0.143 criterion. And this was coming from X-ray crystallography, where they defined the resolution where they have a phase error of 60 degrees. And so when you do this, you get a much higher resolution, and at this point, suddenly cryo-EM became much better. We got much better resolutions. The problem at the time that people didn't realize that this formula, and this only works if the 2 maps are truly independent. And at the time, maps were actually not independent. The way we used to do it, we used our entire particle stack, aligned it to a reference map, got our new orientation parameters, used this to calculate a refined map. We used this refined map to be the new reference map. And when it no longer improved, we split the data set, got 2 data sets, calculated half maps, and then calculated the Fourier correlation. And that doesn't work because these 2 maps are not unrelated, because you always use the same reference to actually align the entire data set. So therefore, these 2 maps are correlated, and we got much too good resolutions than they really were. So what is now called the gold standard Fourier correlation, which is just a normal correlation, how you should really do it, is at the very beginning you split your data set into two halves. You align them to the reference map and then get new refined maps and go back to iterate. And then if it no longer improves, you now separate, you now compare the two maps, and that gives you the gold standard Fourier correlation. Yes? Yeah. That's the way it goes these days. You don't even get a choice anymore. That's the way it goes. I don't think it's as brutally hard as they stated that you have to do it. I think you can be a little bit more relaxed, but it's certainly not a bad thing to do it this way. But you cannot go wrong if you go this way. The reason why I think it's not so hard, so black and white, is when you have a reference that you align your particles to, and you filter your reference to 10 angstrom. And then if you use your 0.143 criterion and you actually still get information here, if you still get signal here, this cannot be influenced by the reference because the reference has no further information beyond 10 angstrom. So if your reference is 10 angstrom and you get a resolution of 8 angstrom, then that is reliable. If your reference is at 5 angstrom and you get a resolution of 8 angstrom, you have to be careful. This could be all reference bias. Do you agree with this? He is much better at these things than I am. So.
If you're beyond the 10 and 8.7 is a little bit close. You usually want to be 40% different or something along those lines. But this is certainly a viable approach.
But you don't get to choose. Rely on and Skarsbok has decided for you. Right?
Yeah, people have done enough analyses that you end up with almost the same alignment of your particles, whether you use the whole data set or 2 half data sets. Back when you were collecting 56 images per cassette, and those 25 were good, and it was really hard to get enough data, this was more of an issue. Now, when you have 1 million particles, you're going to align them just as well whether you're aligning 2 500,000 particle sets or 1 million particle set.
Yeah, and so something that happened in 2016 was a so-called map challenge. At the same time, there was also a model challenge. And I come back to this at the very end. But if you're interested, there's a special issue in Journal of Structural Biology in December 2018. And there are several articles about this map and model challenge. But basically, the main take-home message from that was that even though there is now the gold standard FSC curve, it's still not well enough standardized that you can actually trust the FSC, because it depends on a bunch of other variables, such as the size of the map box, the voxel size, filter, masking, and also the thresholding of your mask. All this will affect how you will get an FSC and what kind of resolution you will get. And so the idea is now that you submit half maps to the archives and they will calculate averages, resolutions for you. So that might be a step in the right way, but people get hung up on resolution, and it's just a number. And it's a good number if you want to improve your methods and so on. But what really matters in the end is the local resolution, which is also said. So what the resolution, the one number tells is just the overall resolution. In my opinion, it doesn't mean much. Because as an example, that's one of our maps. It's an integral head group with a FAB. We calculated the FSC. We got a very nice resolution of 2.8 angstrom. But what is much more important is the local resolution, which was initially done by ResMap, which is now implemented in Relion. And they had a very clever way to actually look at resolution in the different areas of your map. And so what you very often find is that the resolution is a little bit better than your overall resolution in the center of your particles, and it's quite a bit worse in the periphery, where you have much more flexibility. So for fabs, it's very famous that you have these hinge regions, and so the variable part of a fab is usually pretty good, while the constant part of the fab, because it has this hinge, can much more move, and so the resolution will drop right away. But still, the resolution difference between the center here of 2.7 and the periphery of 3.1 is only a difference of 0.4 angstrom resolution. So that's a perfectly fine map everywhere. And so you can pretty much reliably build a model everywhere in this map. And that's what we did. And so at this point, you can really look, for example, at interaction surfaces and which residues interact with other residues. It changes a little bit with other maps like this one. This is a newer map that we calculate. This is the interaction of a complex called CST with the polymerase alpha primase complex. Up here is the CST, and down here is polymerase alpha primase. We calculate the resolution is 4.6 angstrom overall. But now you will see when you look at the local resolution, it's a very different picture. So while, again, the center, the core of your molecule is usually the best resolved, the periphery is pretty bad. And here it's not just 0.4 angstrom, here it's actually 4 angstrom difference. So while in the middle you have about 4 angstrom, here you could just about model a few things, but if you go out to 8 angstrom, nobody's going to model anything anymore, other than maybe the background. So local resolution is a much, much more important criterion than the overall resolution, which is basically just a number.
It seems like only a small portion of the map on the right is even below 5 angstroms resolution proportionally. Why is the overall resolution so high?
Because it has a tendency to like the well-ordered ones. So in this area, everything will correlate very well, and so this gives you a good signal. In the periphery, things don't correlate very well, so it gives you a lower signal. So it tends to like the higher resolution stuff. Yeah, the overall. So it's often a bit optimistic compared to what you have. But this is an extreme case because this is a big complex, so it was easy to image. But unfortunately, this CST is very wobbly aligned to the polymerase alpha, and that's kind of a continuous heterogeneity, and we have a very, very hard time, even with a complex this big, to get a better resolution of the CST, which is very frustrating. Yeah.
There's a little bummer sort of structures in the blue curve. Where's it going up?
Why this dips down? Oh, what?
Like why it's sort of going up at about 1 second. You know, it's going down and then it's going back up a little bit and it's going down again.
You mean this area here?
Yeah.
So that's a good question, and the different things that happen sometimes, often when you have this kind of biphasal resolution curves, is that you have a very well-ordered part and you have a not so well-ordered part, and that creates these kind of weird resolution curves. If you have very few particles, or if you have many particles the same defocus, this can actually be a remnant of the CTF. But that's rarely the case, because usually we have now so many particles that this gets averaged out. So this, to me, would represent that we have a different behavior for the polymerase than what we have for the CST in terms of correlation. Rich, what is here?
The other thing is if your mask is weird, you can often get that as well. So as Tom mentioned before, there's lots of parameters beyond just the 2 half-maps that go into the curve, the number. And so if your mask is too tight, you can get effects like that. If you have 2 domains that are moving very differently, you're essentially having a convolution of a high-resolution CTF and a low-resolution CTF, and it can give you things like that as well.
If you're reading a paper where they've solved a structure using cryo-EM, what might be a red flag to you that, for example, the HIV envelope, like how did they know that they should go back and check their structure?
Because everybody told them, including me.
Okay.
It was totally physically impossible what they did, but they just wouldn't listen to anybody. I mean, it was a crazy situation. There was a guy coming out of atomic force microscopy thinking he knows much better than all the people in the field. I saw the 2 angstrom map, and they had glycosylation coming out of the transmembrane domain, which might tip you off that that might not be quite correct. There were all kinds of weird things in the map and in the structure. And it's just at that time, when they came with 2 angstrom, we all wanted to know, how the hell did you do this? And when they told us what they did, it was clear that it's impossible.
Okay, so like your problem with the detector by just doing some block picking or something, right? Just particle picking without that mix without totally
Yes. And trust me, the referees of the paper told them to do all this stuff, and they've just felt that they know better. The only thing they did in the end was to filter the resolution to 6 angstrom. But there were lots of really good people telling them what they should be doing, and they just thought they know better. It was a very strange, very, very strange blip in the EM field.
But this is why all maps and models now have to be deposited. So if you're reading in front of me on paper and you have any concerns, you go to the EMDB, you download the map, and you can look. If things look unbelievable, they're often are. In this case, it's much harder to get that through than it used to be, because people also use a standard deviation. The best paper in the field at that time was 6 or 8 angstroms per single particle. All of a sudden, there's 2 angstroms. There's so many standard deviations away from whatever I'll say is done. Now, when people make substantial improvements in resolution, 3/4 or 90% of the paper is explaining step by step what small steps they made that were able to make that jump from 1.5 to 1.2. There were 2 back-to-back papers a couple of years ago that explained years of work to make a small nominal improvement from 1.5 to 1.2.
Which doesn't sound much in terms of numbers, but in field space is actually quite a jump. Yes.
What does that resolution difference provide you information-wise?
Very good point. Very good point. So that's what I say. People get hung up on resolution. To me, resolution really doesn't mean much. What is important is what you really see in the map. So getting back to it. So if you have something like this, if you have a map at 8 angstrom, you don't have to give up, because you can still use it to dock in crystal structures. And these days you have AlphaFold 2, so you have a lot of structures that you can dock into your complexes. AlphaFold 2 has really made a tremendous contribution to structural biology. So we could build a model, we could look at, so we found that in this case there was an extension that actually makes this interaction, so we couldn't go onto the sidechain level, but we could still see computation, structural folds that evolve to make this interaction between the 2 complexes. And so, yeah, so Rich already showed you that, so that's a, what do you call it, a test. So what you said, what should be resolved? So if you have 20 to 10 angstrom, what would you expect to see? Exactly, envelope. Maybe domains, these kind of things. If you have 9 to 10 angstrom, what do you expect to see? What?
Parts of secondary structure.
Which part? Which part?
Just like, you might see rods at that point.
Alpha helices. Exactly. You should start to see rods that represent alpha helices. What if you get to 4.8 angstrom? What do you expect to see? Who said this? What's secondary structure? Yeah, you should start to resolve beta sheets. And then when you get to about 4 angstrom, so you expect to see glycine? So around 4 angstrom, what are the biggies? Which are the ones that you're going to see first? Aromatics. You're going to see the tryptophans, tyrosines, and so on. So that's because your map will have very different resolution, different parts. These are the things, if your resolution has to be a certain level, that's what you want to see. And there's a very nice paper by Peter Rosenthal and John Rubinstein talking about this. So, and after all this, now we have a map, and now I'm supposed to talk about validation. And my time is over, so it was not. So I tried to go very, very fast. That took much longer than I thought. So going back to IP3 receptor, you have 4 maps that look completely different. How do you know it's the correct one? And so in 2012, a bunch of the experts met in this meeting and tried to figure out what are the criteria, how do you want to validate your map? And so the first one was, you want to compare reference-free averages with projections from your map. And so this is an example that we had as anaphase promoting complex. So here are just raw particles. These are reprojections from the map, and these are 2D class averages. So if this all fits nicely, then you get a good feeling. However, this only tells you that the 2D data is consistent with the 3D map. It doesn't tell you the 3D map is right. If you're missing certain views, your 3D map might still be incorrect, but it will fit with your 2D data because that's what you use to make a 3D map. And in addition, so that's a good thing that makes you feel good, it's consistent, but you should also look, for example, at the angular distribution of all your particles. You want to make sure that all the space is covered by projections, that there are no big areas that have no projections, and so you don't know what it looks like. So that's good. I would just say you should also look at the angle distribution. Then the tilt pair analysis was actually a really nice test at a time when we were still looking mostly at blobs, and it's a very elegant and easy way to do this. So you collect your entire data set at 0 degree, and then at the very end you take a few images where you first take a 0 degree and then you take another image at a small angle, 20 degree or something like that. And so you first take your 0 degree images, and then you take your tilted images, and you get 2 particle steps. And those images are from the same area, so that you get the same particle in 2 different views. And so now you align these particles to your model that you're trying to test. And from the matching projection, you can now figure out what the angles are of these different projections. And because we know that we only tilted this maybe by 20 degree, the difference between these matching projections should only be 20 degree. And so if you do this analysis, your difference angles, if those turn out to be about 20 degree, you did a good job. You can trust your model. It's very simple, very quick. There's an example, and you can see most of the projections fall into this small circle, but there are certainly outliers, and that's typical because of noise or particle damage or whatever. So never all the particles will be perfect, but the majority should be perfect. And I just want to say that, so you have this in your handout, because I need to speed up a little bit. This map validation is now actually part of the EMDB. You can actually put your data there, and you can do this tilt analysis. Again, this is mostly useful when you are at a level of resolution where you don't see anything and you just have shapes and you want to know whether the shape is correct. The moment you start to see alpha helices, you can be pretty sure that your map is probably correct. So that's excellent. The gold standard FSC we talked about, it's now pretty much default. Then randomized phases, that's actually something that is now used also in all the programs which I learned from Bridge. Because there is a paper, you can look into this, it's actually a very nice method. And it's commonly used, and it helps you to prevent most of your overfitting. And then, as I mentioned, if you have a certain resolution, you expect to see certain features. If you have 8 angstrom, you want to see alpha helices. If you have 4 angstrom, you want to see side chains of aromatic residues. So it's a good way to really look at what you see, whether that makes sense for the resolution. And so just to tell you that this is not so easy, this is a 10.2 angstrom resolution map, so forget the 0.2. But here are some densities that might actually represent alpha helices. But it's becoming kind of difficult to say whether this is really 10 angstrom is not quite ready yet to really resolve nicely alpha helices. And then what I always think is we are humans, we can think, so compare what you get, whether the model, the map actually corresponds to what you would expect from the biology. Any other information, so we, for example, at that time, we made antibodies against all the different subunits. We could then align or basically pinpoint where the subunits are, and we could compare this with interaction map that was done to hybrid in all kinds of different ways. And we could see that our assignment subunits was actually pretty nice with this interaction map. So that helped us to actually believe in this map. And so there are all kinds of things that you can use. You can use to hybrid analysis, pull down experiments, cross-link mass spectrometry has become very powerful. And of course, if you have disease mutations, those you can use. You can do your own mutagenesis, anything to help to really validate the map that you have. And then the best thing, if there are atomic structures known of your subunits, you dock those. And if they fit, it's going to be nice. Again, a long time ago, we did a negative stain of the AMPA receptor. There were crystal structures of homologous domains. And so we could use these. That's a very low resolution negative stain EM map almost 20 years ago. And we could very easily dock these crystal structures into the density map. But the field didn't like us for this map. They thought this is all crap because another structure came out 2 years before that was done with cryo-EM, which is a much better method. You could see much more details, but it was impossible to fit the crystal structures into this density map. And then only recently a cryo-EM structure came out, and it really kind of the same guy who initially worked on this negative stain structure recently was able to do a high resolution structure of this and basically confirming what we got at the time. So this is the bad boy in the field, is the IP3 receptor. And then later on, they did another structure in 2011 at 11 angstrom resolution. So now the IP3 receptor looked like this. But because of the really bad history of this protein, they did pretty much everything they could to verify and validate whether this map is correct. So they made sure that they could see secondary structure elements that should be alpha helices using the potassium channel as a guide. They obviously looked at references, reference-free and template references with reprojections from the map and single particle. That worked out. And then they looked at the tilt test of all these different. And this is the new one, and now you can see this fits very nicely, while all the previous structures, the projections were all over the place. So none of these structures had anything to do with the real structure of the protein. They determined the structure with different image processing programs, and everything looked pretty similar. So in the end, they were actually convinced that this is the correct structure. And then later on, it was confirmed when they got a structure at 4.7 angstrom. Now you could actually start to build the backbone. And then more recently, Rich was able to actually get a really high resolution structure of the IP3 receptor. So now we really know what it looks like. But these days, you not only just get the structures, as Rich said, they were able to get all kinds of conformational changes and see that different receptor subunits had different conformations. So this is really what you are able to do these days. So it's way beyond validating the maps. And so I want to get back as the last point, this map validation challenge. And so what they did was basically they had 7 maps that were in the EMDP. And just to note, this was from rigid particles, so you don't have to worry about local resolution. It should pretty much be all rigid, the same resolution. They gave the data from the Empire archive, and then they basically told them, get us maps out of this. And 27 groups did this. They ended up producing 66 maps. And then they gave this to the assessors that devised a bunch of different ways to actually assess the quality of these maps. And so I just want to talk about one, the apoferritin. And at the initial resolution of the data that was in the Empire was 4.7 angstrom. And now they got 8 maps back from this challenge. One map was pretty much the same resolution as the original one, 4.7, but most of the maps became much better, between 3 and 4 angstrom. And so one thing that they noticed is that when they looked at the map at 3.1 angstrom, which is this one here, and they looked at the map at 3.5 angstrom, which is this one here, there's no difference that you can see. It's exactly the same density. And so from that, they concluded that the current ways that people determine FSCs is not sufficiently standardized, because you can call this one 3.5 or this one 3.1. So you really still have to look after the FSC. And again, this is just the overall number. What you're really interested in is the local resolution. But the main thing that I thought was really amazing was that the assessors found no strong trends. So no matter what software package they used or which workflow they used, there was no correlation to the quality of the map that came out. So what really determined the quality of the map in the end was the choices you guys made, the people, the users, how they decide to do this will decide the resolution that you get in the end. And so they said, in future, what we need to focus on is to basically promulgate best practices, and courses like this here is a good way to actually promulgate these best practices. And so processing of independent data sets, resolution limited alignment, all these kinds of things that we mentioned. And then you should use these best practices and put them into the software, which is actually generally done. So gold standard FSC is already implemented. Resolution limited alignment is implemented. So basically, the point what I'm trying to make, my seminar is not needed anymore, because every map that you got a real map. You didn't need to validate it. It was just according to the resolution that you got. But it wasn't like IP3 that you got totally random maps. If you do the right thing, and if you don't totally mess up, you will get a decent map. And anywhere typically between 3 and 4 angstrom, that's all good. I mean, you will see a little bit more at 3 angstrom than a 4 angstrom, but if you have a 4 angstrom map, you will not misinterpret the structure that you get. I also want to mention that 2 of these structures that came back were at 6 and 7 angstrom. And you might think that is horrible if the data can actually go to 3.5 angstrom. However, this was done with new image processing algorithms, new approaches. And while these approaches have now been used for many, many years, these are totally new ideas how to do this. And if you give those algorithms a little bit more time, they might actually get better than the current ones. So the point is, the good thing is, you're almost never going to be totally wrong if you use the programs like Relion and CryoSpark in a reasonable way. How much you will get out of your data depends on your skill level. And that's what I had to say. So I'm gone next year, right?
Let's thank Tom.
Happy to take questions.
Lena, what's the status of lunch? Sorry to interrupt your question.
This is a case that came up, and one of the faculty members I worked with was reviewing a structure paper, cryo-EM structure paper, and our groups are getting into cryo-EM or all card-carrying crystallograpers. We were looking at these maps, and they were claiming to be 6 to 2 points something. And you can see in some of the maps where the model was docked, nice density, could make out the side chains. The magnesium ion sitting in the middle of it, I scratch my head at to see that. But then on the outskirts of the map, you could easily see the density, where the density was. But it looked like they didn't even bother to fit the model into that density. Is that something like that? Is that common? It really struck me. I told her, I said, just right, say they did a high resolution crystal structure. That look didn't do anything.
I think the problem is that it has become too easy to get EM maps. And so a lot of people who aren't hardcore structural biologists now can use CryoSpark. They hire a postdoc who knows how to run the programs. They get a density map. They dock it in, and then they don't know how to refine the structure properly. And so it's, I think, a little bit, so Rich, for example, after he did low resolution stuff, well, now he did high resolution, but he did a lot of modeling in an X-ray group, and he became really, really good at it. I grew up during a time when we couldn't really model all that much, so I'm much worse than he is in modeling. And so I think the capability of the field has gone faster than the people can catch up with it. And if you're lucky and you have a good mentor, he will train you how to model it. If you are in a biochemistry group and you're the only person doing cryo-EM, and you have never really modeled yourself, then you do the best you can. But it might be a problem. But we all try to do our best. I think that's a fair assessment, but our best is not always as good as X-ray crystallographers who have done this for decades.
What just struck me is that it looked like the high resolution, I think it was fairly hard structure of this thing.
Trust us, we sometimes look at models and density maps and get embarrassed. It just piezo was a case.
Looking at the map and if the density was correct for what they were giving us, you could easily build, there was subtle shifts with the backbone.
So we would like to do that. There's no reason for us not to do this. This is not a difference between cryo-EM and X-ray. It's a difference between who does it, the work. But we can get embarrassed.
That stresses a lot of crystallography.
But there are also famous cases in X-ray crystallography where things have not been that great. It's just the person who does it.
Oh yeah, I give you the list.
Yeah. Which is what?
What's phase randomization?
Phase randomization. So I show the images and Rich explains it.
Next slide.
This one or the next one, which one do you prefer? Huh?
This one's much easier. So when you calculate your reconstructions from two half maps, you have this mask. Remember I was saying that this mask has information in it, and that mask information can influence the British correlation because both maps have been subjected to the same mask. And so the way that you can limit the effect of the mask is by going to a particular resolution and in your data set, assuming that, so in our reconstruction vehicle, phase and amplitude, you could take the amplitude information, keep it as is, but take the phases and just randomize that from 0 to 360, rather than whatever value they should have been in the map. Then you know that that should have no correlation because remember, we're trying to calculate the cross correlation between phase and amplitude, If you've taken your phases and entirely randomized them, there should be no correlation. The only correlation that's still there is the one that's imparted by the mask itself. And so by using the phase randomization, you eliminate much of the effect of the mask on the alignment of the two FSCs. And so that's why you can get rid of overfitting. And so if your mask is extremely tight, you can have a very strong effect of that on through the autocorrelation function on your density map. If your mask is very loose, it's going to be weak. And this normalizes that effect. So if you have a really loose mask, it's not influencing your FSC. If you have a very tight mask, it isn't. So if you look at the red dotted line, the FSC curve looks like it's much further out. It looks like it goes to much higher resolution. But when you do the noise refinement and get rid of all of the information, I guess past 17 angstrom in the phase and recalculate it, you can, and then subtract that from your actual information. So what they're doing is they're subtracting all of the information that is maintained after phase randomization from the information that's there without phase randomization. If there's no effect of the mask, then your phase randomized values will bottom out at 0 because there's no information left. If your mask has a strong effect, then there'll be information between 0 and 1. And you can subtract the information between 0 and 1, and that will give you the true signal.
So this is why this is still being used, but that's not what they showed here. Here they just did reference bias. They just cut the reference at a certain resolution, but that is not really useful anymore. But what you say, it's a very good way to look at the effect of masks. So it's still very useful and it is implemented. But the reason they did it at that time was to show reference bias. Because if you have a reference that goes to 7 angstrom and you use this, all the information up to 7 angstrom will be correlated to the reference, even if the maps themselves don't really have information. So that's why you get some correlation even beyond what your data shows. But if you cut off at a lower resolution and randomize the phases, there should be no correlation between the two halves of the map. So if you still get correlation, it's all correlation to the reference and not between the two maps. And you can get rid of that by randomizing the phases up from. But that is long gone. Everybody will resolution filter the reference. But another effect, the mask, we cannot get rid of. We all have to mask. And so this also helps you to look at the effect of a mask on your final volume.
So you brought up kind of benefits of using AlphaFold for docking. Can you talk a little bit about other times that AlphaFold might benefit the data analysis or processing, or times that you don't want to use it at all when it might introduce bias?
So if you use AlphaFold, you will never take the full resolution. You will always just cut it down as far as you can, maybe 15 angstrom, 30 angstrom. So you only want the shape, you never want to bias towards the model. So it's basically mostly, you can use AlphaFold as an initial model for your protein. I don't like to do that because you put a lot of assumptions in your data set. I think you should always start with your data set and get the references and the initial models all from your data set. So for that, I wouldn't recommend using AlphaFold.
So you wouldn't use it for a template, so you go back.
I personally would not do that. You really want to know what the data has to tell you. And I can tell you from a very painful example. This one, we made a really stupid mistake. We didn't use AlphaFold 2, but we knew what alpha polymerase looks like and the primase, and we used this, unfortunately, as our reference because we know that's the complex. It just binds the CST complex. So we can use this as our template to go and pick particles. The problem is what turned out later on is when CST binds to the polymerase, it actually changes the conformation, goes into an active state, which was totally different. So with our stupid X-ray template, we didn't pick up any of those particles. It turned out okay because other people did that, and what we found here was actually the recruitment state. But it's really, I cannot emphasize this enough, and I feel very stupid that I didn't listen to my own advice. Don't use foreign templates. Use your own data to see what your data tells you. But again, for this one, we had only a single experimental structure for the polymerase primase complex. It was a horrible structure. It was actually, some of these, the clash factors were horrendous. And what we did here, for example, was to replace this one subunit by an AlphaFold model and put it back in and use it to do the model building, as a start for model building. So I try not to get too biased from AlphaFold. I think it's great once you have a map yourself to help you with the modeling and guiding. And sometimes you can actually see difference between AlphaFold model and your model, and you see what changes when things bind. But it's great to have AlphaFold to actually, especially very often you get to about 4 angstrom, and it's not easy to model. So having AlphaFold model to help you is very helpful. What else do you use AlphaFold for?
It can be really helpful for identifying components. So if you have a heterogeneous complex and you don't know what's missing, often you can dock in AlphaFold and you'll see either a domain is missing or a subunit is missing from your density map. And it may, you can go back and look at your DELs. If it's still there, that means maybe it's not binding or you're in a conformation where that is too disordered.
So in single particle, can be done, but where it's really used exactly this way is in tomography, where you have very low resolution maps, around 8 angstrom, and you can actually do model building in AlphaFold and then fit it into your tomograms. There, AlphaFold has been extremely powerful.
How good is actually AlphaFold to predict, let's say, oligomers and complexes? Because like if you look at their database, they just used the single protein sequences for the structure prediction.
There's a new version that came out that looks now in complexes and oligomers, and it's bloody good. I have nothing bad to say about AlphaFold.
Also, that's the AlphaFold 2? Or?
It's AlphaFold 2 multimer. It's amazing. AlphaFold 2 is amazing. Too good.